Hello, ladies and gentlemen. This is one part to two-part series tutorial. We're going to go ahead and look at this, but we need to go ahead and go over some basics before we get into this. And one of the basics that we need to go look at is something called Fibonacci numbers, Fibonacci series, or Fibonacci sequence, however you want to call it. Now, we're going to go over several things. Now, first off, what is the Fibonacci sequence? Well, it's very, very simple. It's a pattern. First, we start with two numbers. And this is the first number and the second number, so that's 1 and 1. Then we go ahead and take these two previous numbers and then add them together, so we get the next number in our sequence, which would be 2. Then we go ahead and take the 1 and the 2 and add those two together, and then we get the next number in our sequence. And we just go ahead and keep on doing that until we get to on to infinity. And it just works like that. And then we just keep on going, so on and so forth, all the way to infinity. And these are also known as Fibonacci numbers. So that's how we start our Fibonacci sequence. We start with the first two numbers, 1 and 1, 2, 3. And you're probably wondering, why am I going over this kind of sequence? Well, it's very important because we're getting into something called recursive algorithms. So recursive algorithms are algorithms that rely on previous information to go ahead and move on. Linear equations can be expressed in recursive algorithms, but also a whole bunch. But there are some numbers and some things that we cannot that are very difficult to express iteratively rather than recursively. So, but we won't be working with those for a little while, but we'll see that. And one of the main things is that we have to work with this. If we're going to go ahead and make our sequence, we have to make sure we have something called a list or an array. So I put all the numbers into this list or an array, and you're going to go ahead and look at this. So I'm just going to go ahead and start off with our Fibonacci sequence. Let's see, a plus 13, 21, I think. Well, yeah. And we're going to keep on going after that. I could be wrong about that 21. Let me make sure. Not only did I confirm that that's 21, but then I also got the next couple of numbers in our set. Now, we're going to go ahead and look at also the positions. So we're going to start with this right here. This is position 0 because that's the first number in our sequence. I should start with position 1 because usually you start with that. But for now, we're going to go ahead and work like this because I'm a computer scientist and we always started with 0 when we go ahead and look at a sequence. So this is position 0, this is position 1, position 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is how these positions work. Say for instance, I'm looking at position 1 in my array A. So we're going to use something called A sub n. N stands for the number in these positions. So these numbers right here would be any of these over here. We can use any of these. So in other words, if I had A sub 5, I want number 8. So I'm going to go ahead and put down 8 for that. And we're going to be using this to go ahead and solve for these kind of sequences. So now, to be able to write this into a recursive algorithm, we're going to be using this notation. So this is what we're going to use this type of notation. So let's see. So there's a couple of things we have to know. What is in our list before we even start? So we're going to go ahead and imagine I don't have this first list. I have an imaginary list right here. I don't have all my numbers yet. I just have the first two, 1 and 1. Now, the way recursive algorithm works, you're going to go ahead and use whatever memory or whatever numbers you're given to go ahead and make your sequence. So remember that this is position 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So This is the way this works. I'm going to go ahead and formalize this a little bit because right here we just went ahead and looked at everything right here. So originally, if we take a look at our original numbers, when we go ahead and look for position A sub 2, we took 1 and we added 1. I'll go ahead and move that down here, make it a little bit bigger so we can actually take a look at that. Alright, that almost looks like a D. It's supposed to be an A. Don't worry about that. So, what do we do right here in these things right here? So, basically we took A sub 2, that's equal to A sub 1 plus A sub 0. So when we start to formalize this even more, we're going to go ahead and start working a little bit backwards. And we're going to be using these numbers to go ahead, this number right here, to go ahead and generate this one and this one. So that way we can go ahead and put this together. So how did we get A equal to 1, this little thing right here, 1 from this 2? Well, we can simply just use some subtraction. 2 minus 1 gives us that particular 1 right there. And then for the other one, we have A, well, this is 2 minus 2. So say, for instance, we change this to n. So this one and this number right here would also change into n. So we have A sub n. Let me move this up a little bit so people can see. Equal to A sub n minus 1 plus A sub n minus 2. Doesn't mean that we're going to go ahead and take the A and subtract 2 from that. We're not going to take the A and we're not going to subtract 1 from that one. We are going to apply the numbers that we have right here. So just taking a look at this stuff right here. So we have our previous memory. This right here is the stuff we're going to go ahead and use for the configuration. A sub 0 is equal to 1. A sub 1 is equal to 1. And then our formal part of this is the recursive part of our definition. A sub n is equal to A sub n minus 1 plus A sub n minus 2. And this will go ahead and formalize our thing right here. So this is for recursive. This is recursive algorithms right here. And you can use this beyond there. So say, for instance, just to go ahead and see parts of the sequence, I want to go ahead and find what A sub 2 is. That's equal to A sub 2 minus 1 plus A sub 2 minus 2. Alright, so where was I? So I have this right here that says A sub 2 minus 1. So A sub 2 minus 1 is A sub 1 plus A sub 0. It's equal to A sub 2. So now I look at our sequence. These are the two numbers, so I just plug in 1 and 1. A sub 2 is equal to 2. So I can just plug in 2 right there. Now you're probably wondering, well, why are you doing all this work? Why is it something that you need to do? Well, actually it's because this is really, really important for our sequences in the end of everything else, because how can I explain it? Well, it's just more formal this way. This is the way we do it formally, but we also need it to go ahead and make sure we understand our instructions. These are very, very, very clear instructions, especially after you get used to them, especially when you're doing computer science. I'm a computer scientist, so this makes a lot of sense to me. So A sub 3 is equal to A sub 2, let's see, A sub 3 minus 1 and A sub 3 minus 2. So that goes the A sub, so that goes the A sub 2 plus A sub 1. This is going to give me A sub 3. So A sub 3 is equal to, let's see, we have the numbers, so we have 1 plus 2. And that would give me A sub 3 equal to 3. Alright, So yeah, as you can see, you can have this right here, and actually it makes a lot of sense, especially if you're working with something like, let me see, Excel. I'll show you in Excel in just one moment. All right, so we were looking at this part of our equations and everything we have here, but also I wanted to go ahead and talk about using Excel to do this. Now, Excel is really great with recursive algorithms. It is one of those systems that actually uses it optimally and actually does it really well. So this is what we do. I hit the equal sign that tells the computer that I'm going to be applying formulas to our system. I'm going to go to this position. This is A sub 2. So I'm going to go ahead and put add because that was part of the sequence. And then we go to the next one and we're just going to push enter. So in other words, I have in this cell equal to A2 plus B2. Now as you can see, it automatically added everything. And if I want to go ahead and continue this going on to the left, I can really do this. So let me see. I'm actually going to do something also. I want to see what the positions are. I want to put down what these positions are. So number one, I'm going to make these a different color just so you can see that these are different. And then I'm going to be adding, I'm going to take the previous number plus 1. That way it adds it. And if I go ahead and just take my cursor and put it over this little square at the lower right hand corner of that little box and just drag it to the side, I automatically have numbers that go up. Now, if I do the same thing here, it's going to go ahead and apply the same thing. And you can see as the sequence started moving on, it's exactly what we had before. All right. And as you can see, 89 was our last number. So these are Fibonacci sequences done through Excel. This is just like saying that this was, let's see, A sub 1, this one A sub 2, A sub 3, and then so on and so forth, all the way down to A sub 10. So you have to see how that works, and that's the basics to the Fibonacci sequence. Fibonacci sequence is one of those things, and it's a recursive algorithm. Very important that we go ahead and do this. The reason for that is because if you take a look at this sequence, it's really hard to make this as a iterative or something that's going to have a linear or just a formula that will give us the next number in line. But we can go ahead and use recursives to express linear equations, exponential equations, and all sorts of other things. But it also helps us with something called finance, and we'll see that later on, especially with credit cards. All right, I'll talk to you later and answer the